All right. Classify each of these as a change of state or merely a change of shape. When you chop a log into kindling, all you do is change its shape. You haven't changed its state, right? When you boil water, change state, right? It goes from liquid to gas. When ice cream melts, whose fault is that? It's your fault because you should have eaten it fast. Ice forming in a freezer, change of state, right? Because it goes from a liquid to a solid, right? Cutting dough into strips. All you do is change in the shape, right? It's still dough. Now, chemical properties are different than physical properties in that you must perform a reaction in order to see the change. Now, we may talk about food a lot today, because we're going to talk about calories later too, and energy. But if you like to cook, it's a great example to understand chemistry for a lot of things, okay? And I think baking a cake is a perfect example to talk about the difference between a chemical and physical change.
Are you craving cake?
No, I had a piece last night.
You're just thinking about that?
No, I wasn't, but you know, it's a great example. I like to cook too. So, now, when you take and you kind of mix everything up together at the beginning, what kind of change is that? This is like a physical change, right? There's no chemical reaction really going on. But when you put it in the oven and you put some energy into it, what happens? It rises. It changes the way it looks. And it certainly changes the way it tastes, doesn't it?
Yeah.
That is a chemical change. A chemical reaction is going on. Then when I take it out of the oven and I cut up into pieces, that's just a physical change, isn't it?
Mm-hmm.
Okay, see the difference? Okay. So a chemical change takes place anytime you form one or more new substances. You have to form a new substance. Water vaporizing doesn't form a new substance. It's still H2O. Okay? We'll talk a lot more about chemical reactions. That's what chemists do, right? Chemical reactions. In my last class, they said, most of them said they never had flan before. And I said, poor children. Flan's good stuff, isn't it?
Yeah.
Huh? You don't like it?
It has a weird texture.
It does have an unusual texture, but if you like custard and stuff, it's like the bomb.
But it's not like ice cream custard.
No, it's different. Yeah, it is different. And when you caramelize that sugar on top of it, did that sugar, was that a chemical or physical change to that sugar?
A physical change.
Y'all know what caramelizing the sugar means, right? They put the sugar on it, and then they put a torch on it and makes the sugar turn brown.
Yes.
Kind of like creme brulee.
Well,
Same thing.
If you created caramel, I guess it would be.
That's a chemical change, right? It absolutely is. Most cooking involves chemical change, unless you're just like heating up green beans in the microwave. That ain't nothing. You just put a little bit of energy. But when you turn that sugar from being white into being brown like that to make caramel, that is a chemical change. You have a new substance there.
And it's extra yummy.
And it's what?
Extra yummy.
It sure is. Absolutely. So, classify each of the following properties as physical or chemical. Ice melts in the sun. Is that physical or chemical property?
Physical.
It's physical. It doesn't change the fact that it's water, does it?
Nope.
Copper is shiny.
Physical.
Physical. Nothing to do with reaction. Paper can burn. That's chemical, because when the paper burns, I don't have paper anymore, do I? Okay. A little bit of ash, but mostly carbon dioxide water. A silver knife can tarnish. This one's a tough
I
one.
want to say
Does
chemical because it,
anybody know what tarnishing is?
yeah, it's when oxidation gets.
It's oxidation. That's a chemical reaction. When oxygen reacts with the silver and it forms that kind of layer on top of it, then you got to take some other chemicals and make it go back to silver, right? It's a chemical change. It's an oxidation of the silver. When a magnet removes iron particles, does it change the fact that they're iron particles?
No.
So it is purely a physical change, right? Okay. I'm gonna have to move this thing up closer. Classify each of the following changes as physical or chemical. When you burn a candle,
Physical.
who says physical? Raise your hand. Who says chemical? Now, it says burn the candle. It does not say melt the candle. Burning is a chemical change. Now, what happens when you light a candle? Here's what happens. It melts the wax, and the liquid wax goes up the wick, and then it burns. It changes it. At the end, you can't just stop burning and still have that candle right there, right? It doesn't just change back into being a whole candle, does it?
No.
It's gone away somewhere. Where did it go? You form CO2 and water vapor. Anytime you burn something, you form a lot of CO2 and water vapor. Okay? So, when you burn the candle, not just melt it, when you burn it, that is a chemical change, okay? We'll talk more about burning and oxidation and all that stuff. Ice melting on the street, what do we say about ice melting? That is physical, right? It's still water. Whether it existed as ice or liquid, it's still water. Toasting a marshmallow. Is that marshmallow, when you set on fire, is different than when it was started, right? It tastes different, doesn't it?
It's a lot more feeling on the inside.
Well, the inside doesn't do a whole lot, does it? The inside just gets hot and kind of melts. But the outside, that brown crust on the outside, just like the flan, right? Well, if you do it right, you don't really set it on fire, but it's kind of fun to set them on fire, isn't it? At any time there's fire involved, guaranteed that's a chemical change, okay? When I cut a pizza up,
Physical.
that's just physical, right? I'm just cutting it into pieces. Didn't change the fact that it's pizza. Didn't change the way it tasted. It's just pizza. Iron rusting on an old car.
Chemical.
It's chemical, because iron rusting is a lot like silver tarnishing, right? Same thing. Rust looks a lot different than it did before it started to rust, right? We've all seen rusty stuff before. Okay. If I fall off this table, somebody pick me up. All right, temperature. What is temperature? That's the first question we gotta talk about. It's a measure of kinetic energy. Yep. I hate this definition up here. This a measure of how hot or cold an object is compared. That's terrible. That definition sucks. Most chemists would not use that definition. Most people, when they think about temperature, that's what they think about, when it's hot or it's cold. But guess what? Y'all watch those people in football games, they're out there, it is, you and me, we'd be like, oh, that's too cold. They're out with no shirt on. They must not think it's cold, right?
They've been moving around.
Hot and cold are relative terms. They're not good for defining temperature, okay? Temperature really is an indicator of how much energy something has. The more energy something has, the higher the temperature, okay? I.e., let's go back to water. Who's ever put water on the stove and boiled it? Make pasta, right? You gotta put some water on the stove and boil it. What happens to the water when you put it on the stove?
Starts to boil after a while.
After a while. Why does it start to boil? Because the amount of energy in the water goes up. And how do you measure how much energy the water has? With a thermometer, you can measure what the temperature is. As that pot sits there longer and it gains more and more energy from the stove, the temperature goes up. We're not measuring heat, we're measuring energy. Okay? So we're actually measuring energy. Now the problem with temperature is that we have 3 different temperature scales. We have Fahrenheit, Celsius, and Kelvin. And fortunately for us, we live in the United States, so we get to use Fahrenheit all the time, right? Guess what? We don't use Fahrenheit in this class. What do we use in this class?
Celsius.
Or?
Kelvin.
Yep. We will use both of those, okay? At certain times, you'll be required to use Kelvin. Other times, it won't matter if you use Kelvin or Celsius, okay? How do these three temperature scales relate to each other is a good question, okay? So here we go. Let's look at the one in the middle. Let's look at Celsius, because it's the easiest to understand. Water boils at what? 100 Celsius. We're talking about Celsius. 100 Celsius. And it freezes at what? 0 Celsius. That's pretty easy to remember, right? 100, 0. All right, what about Fahrenheit? Oh, it boils at 212 and it freezes at 32. All right, well, that's not very useful. Fahrenheit scale was originally based on body temperature. Lord Fahrenheit derived the scale, and he said 100 degrees Fahrenheit was body temperature. He didn't have very good measuring devices. He was off a little bit, right? It was a long time ago. You can forgive him, right? It's okay. So that's what Fahrenheit was based on, but in the lab, that's not very useful for us. So look at the difference between 212 and 32. That's 180 degrees, right? Here, it's only 100 degrees. Now, for Kelvin, it's based upon an absolute temperature where there's zero energy. Zero energy would imply 0 Kelvin. And for Kelvin, water melts at 273 Kelvin and boils at 373. So note that this difference right here is the same for both. It's 100 Kelvin or 100 Celsius. They're parallel to each other, right? It's just an offset. Does that make sense? No. Look, at 0 Celsius, it's 273 Kelvin. At 100 Celsius, it's 373 Kelvin. So the difference between melting and boiling is 100 on both scales, right?
Yeah.
And we're going to show you how to convert between the two.
I have an interesting question.
Yes.
Is this Kelvin scale the same one used to measure light temperature?
Light temperature. Light doesn't have a temperature.
Lights,
On fluorescent lights?
daylights, yeah.
Why would you want to know the temperature of that thing?
Because when you're doing film work, you have to figure out how to light your set properly.
Yeah, you can either measure it Celsius or Kelvin. The two are parallel to each other. How you report it is different. It just doesn't matter.
Like some
It depends upon
temperatures
whatever.
are going to be, a certain degree Kelvin if they're more blue than others and stuff like that.
Yeah, sir. The different lights will give off different amounts of heat depending upon what's inside. Yep. That makes sense. So, at what temperature does water freeze? Does it freeze at 0 Fahrenheit?
No.
No.
No, because 0 Fahrenheit is below freezing, isn't it? Does it freeze at 0 degrees Celsius?
Yes.
Yes, that's what Celsius is based on, right? Okay. 0 Kelvin is nothing that we're talking about yet. What is the temperature at which water boils? 100 Fahrenheit?
No.
I hope not. Why not? Does it get up to 100 Fahrenheit in Sanford in the summertime?
Yeah.
If it was boiling, then when you go outside, you would boil, right?
Yeah.
It feels like you're boiling, but you're not really.
Right now.
You're not really boiling. Okay? Does it boil at 32 Fahrenheit?
No.
That's where, what does it do at 32 Fahrenheit?
Freezes.
Freezes. So the only answer we got left is 373 Kelvin. Okay? Note that it's not degrees Kelvin, it's just Kelvin. Okay?
What is that?
It's because it's an absolute scale. You don't have to have degrees. How many Celsius units are between the boiling and freezing points of water? What do we say?
100.
100, right? That's why it's useful. Just like the metric system, tens and hundreds, right? So there's 100 degrees between boiling and melting.